Howdy. This video is on the nomenclature of isotopes and subatomic particles. To be able to understand nuclear reactions and radioactivity, you need to understand the symbols used to represent isotopes and subatomic particles. After watching this video, given the symbol of an isotope or subatomic particle, you should be able to determine what it's composed of. You should be able to identify the symbols of isotopes or subatomic particles. You should be able to identify the differences and similarities between the different types of radiation. For example, which is the most penetrating, the most dangerous, and the fastest. And so atoms have a diameter of roughly 10 to the minus 10th meters, which corresponds to an angstrom. In the center of atom is a nucleus, which has a diameter roughly on the order of 10 to the minus 14th meters. And inside the nucleus, you have nucleons, which are protons and neutrons. Now, the protons and neutrons are actually composed of quarks. Each has 3 quarks. A proton has 2 up quarks and 1 down quark. A neutron has 2 down quarks and 1 up quark. I should also remind you that at the very small scale, things behave very strangely. And so please remember that protons, neutrons, electrons, quarks, they all have wave-like properties. They are not little spheres. There are 4 fundamental forces in nature: the strong force, electromagnetic force, weak force, and gravity. The electrostatic interaction is part of the electromagnetic force. It is most of chemistry. And so atoms are formed because of the electrostatic interaction. Molecules are formed because of the electrostatic interaction. The strong force is what keeps nuclei together. Protons are repulsed by each other based on the electrostatic interaction, and they're attracted to each other based on the strong force. Because the strong force is stronger than the electrostatic interaction, that's why protons are together in the nucleus. And so chemical reactions are about the electrostatic interaction. Nuclear reactions are about the strong force, which is why nuclear reactions can involve dramatically more energy than chemical reactions. The strong force is much, much stronger. And so if we look at the subatomic particles, we have protons, neutrons, electrons. Protons have a +1 charge, neutrons are charged neutral, electrons have a -1 charge. Also, please notice that electrons are over 1,000 times less massive than protons and neutrons. And so I mentioned that protons and neutrons are made up of quarks. An up quark has a charge of 2/3, a down quark has a charge of -1/3. And so a proton is composed of 2 up quarks and 1 down quark. So 2/3 plus 2/3 -1/3 gives us a charge of +1. Neutrons composed of 2 down quarks plus 1 up quark, so -1/3 -1/3 plus 2/3 gives us charge neutral. And so nucleons are held together by the strong force. So it's the strong force that keeps the quarks together. Nuclei are held together by the strong force. And so the strong force keeps the protons and neutrons together. The strong force is carried by the gluons, just like the electrostatic interaction is carried by photons. The strong force only acts over short distances. And so if one proton's up quark changes into a down quark, then the proton changes into a neutron, and you have one element change into another element. And so this is an example of positron emission. It's kind of interesting. You can think about nuclear reactions on 3 levels. And so often an up quark will change into a down quark, which means a proton changes to a neutron, which means you go from one element to another element. If a neutron's down quark changes into an up quark, then the neutron changes into proton, and again you're going from one element to another element, and this is an example of beta emission. And so some isotopes of carbon, you have carbon 11, 12, 13, and 14. And so isotopes of the same element have the same number of protons, same number of electrons, just a different number of neutrons. And so the only thing that's really different is the mass. Because the chemistry is based on the number of protons, the chemistry for the isotopes should be very, very similar. And so an atom of a given element that different number of neutrons are called isotopes. Isotopes of the same element have nearly identical chemical behavior. Their mass is just a little bit different. Isotopes are often used instead of kinetics. And so basically what you could do is if you have a reaction that involves carbon 12 is the most naturally abundant isotope of carbon. But if you change a carbon to carbon 13 or carbon 14, you can actually monitor it during the reaction and see from what molecule to what molecule it went, and you can use it to understand the mechanism for the reaction. By given the number of protons and neutrons, you should be able to determine what isotope it is, and given the isotope, you should be able to determine how many protons and neutrons it has. Now, if you look on the periodic table, you have these little boxes. The top number is the atomic number, which is the number of protons. Then you have the symbol, and then the bottom number is the atomic mass. The atomic mass is a weighted average of the atomic masses over all the isotopes. And so for carbon 12 is the isotope with the largest natural abundance. So most carbon is carbon 12. And so that's why its atomic mass is so close to 12. It's 12.01. And so you can be asked, how many neutrons does the most common isotope of oxygen have? And so again, this 8 means it has 8 protons. That's the atomic number. The 16 corresponds to the number of protons and neutrons. Again, it's a weighted average, but it's really close to 16, so we can assume that the most common isotope of oxygen is 16. 16 protons plus neutrons. And so 16 minus 8 would give us the number of neutrons. Right? So all we have to do is take the mass number minus the atomic number, and that gives us the number of neutrons. This one's a little bit more difficult. Here your mass is 55.84, which is closest to 56. So we can assume that the most common isotope of iron has a mass number of 56. So that would be the number of protons plus number of neutrons equals 56. 56 minus 26 gives us 30. And so you'd expect that the most common isotope of iron has 30 neutrons. Now, if you look at the elements in red, these are all man-made. They do not occur naturally. And if you look closely, you'll see that instead of masses listed like in the other ones, you have these square brackets. And that corresponds to the most common isotope. I should also mention that all elements after uranium are man-made. And so uranium is the heaviest naturally occurring element. I should also mention that everything after bismuth is radioactive. And so you go polonium down here, and then down to the lanthanide series. And technetium and promethium, they have no stable isotopes. It's also kind of interesting. Hydrogen and helium are the most abundant elements in the universe. Hydrogen composes about 70% of the universe, helium about 28%. And so hydrogen, helium, and lithium were created during the Big Bang. All other elements were created by nuclear reactions. And so this is kind of a cool periodic table, actually indicates what type of nuclear reactions or where the nuclear reactions occurred that created these other elements. And so again, we see that blue corresponds to the Big Bang. You see that some helium was also formed from dying low mass stars or from exploding massive stars. Oxygen and fluorine, neon came from exploding massive stars. You had exploding white dwarfs produce some of these. So again, kind of interesting. After the Big Bang, you had hydrogen, helium, and lithium, and then everything else was created by these nuclear reactions. And so for an isotope, we can symbolize it by carbon-12. And so carbon, all isotopes of carbon have 6 protons, so we don't need that number here. But if we're balancing nuclear reactions, we want to make sure to include the atomic number. Because what we'll see is that when you balance nuclear reactions, you have to make sure that the sum of the mass numbers products reactants are the same, and the sum of the charge products reactants are the same. And so the 6 is the atomic number. It's also the charge of the nucleus. And so we can represent carbon-12 using this way or using this way. Please remember that electrons are 1,000 times less massive than protons and neutrons. The electrons still have mass, but they're not included in the mass number. We can also indicate carbon-12 using this nomenclature. And so you should be able to go from the symbol to the mass and the charge. And again, this is the charge of the nucleus. And so here we have tritium. And so you have a +1 charge. You have 1 proton in the nucleus. The mass number is 3. And so that actually gives you 2 neutrons. So make sure you can go from the mass and charge. You should also be able to go from the protons and neutrons. And you should be able to go from the proton and neutrons back to the isotope. And so carbon-14, all isotopes of carbon have 6 protons. That's the atomic number. 14 is the mass number. It's the number of protons plus the number of neutrons. So 14 minus 6 means we'd have 8 neutrons. Now this is kind of interesting. So the X corresponds to some element symbol. It doesn't have to be the same symbol. And so we can ask ourselves, of the pairs of the nuclei above, which pair has the same chemical properties? And so the chemical properties are dominated by the number of protons. And so this pair here both have 6 protons. And so they should have basically the same chemical properties. Which pair has the same mass? And so that's the number on top. So that pair there should have the same mass. And which pair has the same number of neutrons? And so 14 minus 6 gives us 8. 15 minus 7 gives us 8. Now, a stable isotope is one that does not spontaneously decompose into another. And so by spontaneous, again, we just means occurs without any outside intervention. And so a stable isotope does not decay into another isotope by itself. A radioactive isotope is one that spontaneously decomposes into another. And so again, we don't know how fast this is, but we know we'll look. Now, the three most common forms of radiation are alpha particles, beta particles, and gamma rays. Now, often it's said that alpha particles are high-energy helium-4 nuclei, which used to really confuse me as a student. But it turns out that 2 protons plus 2 neutrons are very stable. And so 2 protons plus 2 neutrons compose helium-4 nuclei. 2 protons plus 2 neutrons also compose alpha particles. Beta particles are high-energy electrons that originate from the nucleus. Gamma rays are very short wavelength, high-energy electromagnetic radiation.
The British scientist Ernest Rutherford was one of the first to show that radioactivity could consist of 3 distinct types of radiation. The 3 types differ in their response to an electric field. A source of radioactivity is passed through a hole to form a beam. The beam is directed at a fluorescent screen, which is illuminated when it is struck. In the absence of an electric field, all the radioactivity beam strikes the target at a single point. When an electric field is applied, the initial beam is separated into 3 components. One of these is deflected upward by the electric field, indicating that it is negatively charged. These radioactive emissions are called beta rays. A part of the beam is deflected downward, indicating that these particles are positively charged. These radioactive emissions are called alpha rays. Notice that the alpha particles are deflected less than the beta particles by the same electric field. This occurs because the alpha particles are more massive, but the amount of deflection is also determined by the relative energies of the different types of radiation. The portion of the original beam that is undeflected is due to radiation that is not charged. These emissions are referred to as gamma rays. Other experiments showed later that the beta rays are actually high-speed electrons. The alpha particles proved to be helium nuclei. The gamma rays are high-energy photons, analogous to X-ray.
So kind of cool, he's able to separate the types of radiation by putting it through electric field. The beta rays, because they're composed of electrons and are negatively charged, were attracted to a positive electric field. The alpha rays, which are 2 protons plus 2 neutrons, have a positive charge and were attracted to the negative electric field. And gamma rays, which have no charge, are just electromagnetic radiation.
Materials give off energy, especially if we expose this sample to ultraviolet light. We can see it glow. There are 3 different types of radioactive particle energy. There's alpha radiation, beta radiation, and gamma radiation. Here we have a nuclear scaler that measures radioactive decay. Each click that you hear is a nucleus of an atom that is decaying by giving off a radioactive particle. This is a Geiger tube, and it has a window that allows the radioactive particles to pass and records them on the nuclear scaler. What we'd like to do in this demonstration is to test our samples both for penetration and also for the distance that you must be away to receive any protection. Let's place a beta particle in our sampler. We notice that there's a slight increase in the counts. The background radiation is not nearly that fast. Here we have some small sheets of lead that we'll place there to provide some screening. We notice that even one lead sheet dramatically cuts down on the beta radiation. 2 and even 3, and we're down now to quieting the counter back to background radiation. Let's see if that also works for gamma radiation. We'll change the sample. We notice immediately that more energy comes from the gamma. 1 sheet of lead and 2 and even 3 that quieted the beta does not quiet the gamma. We can add even a 4th. Gamma has the greatest penetration of all the radioactive particles, alpha and beta.
And so it's kind of interesting. Not all radiation is the same. Gamma is able to penetrate more lead than, say, beta particles. Alpha particles can even penetrate less. And so both alpha and beta radiation are accompanied by gamma radiation because the new nucleus may be formed with its nucleons in a high energy arrangement. The gamma ray photon is emitted when the nucleus settles down into a state of lower energy. And so for most radioactive decays, you'll actually emit more than just one type of radioactive particle. I should also mention the video misspoke saying that those were the 3 types of radiation. There's actually more than 3 types of radiation. It's just that alpha, beta, gamma are the most common types of radiation. And so other types of nuclear radiation include neutrons, protons, and antiparticles. And so an antiparticle will have the same mass but the opposite charge. And so there's anti-electrons, anti-protons, anti-neutrons, etc. It's actually kind of interesting. Physicists have even made an anti-hydrogen. Now, when a particle interacts with its antiparticle, actually the mass is converted into energy. And so alpha particles, 2 protons plus 2 neutrons, they're not very good at penetrating. But once they get inside your body, they can cause a lot of damage. Beta particles can go through your hand, go into aluminum. Now, the alpha particles and beta particles, they're both charged species. The alpha is positive charge, the beta is negative charge, and that's why they aren't very good at penetrating. Gamma rays are able to go through your hand, through aluminum, into lead, as we actually saw in the video. Neutrons can go through your hand, through aluminum, through lead, and through concrete. Neutrons are very penetrating. The gamma particles, neutrons, are the most penetrating. And again, you can think about it in terms of the charge. The bigger the charge, the less penetrating because it will be repulsed by electrons or by nuclei. And so electrons and positrons are 1,000 times less massive than protons and hence are not included in the mass number. And so the positron is the antiparticle for an electron. And so these are some of the subatomic particles. And again, please make sure you can go from the symbol to the mass and the charge, and from the mass and the charge to the symbol. And again, when you're balancing nuclear reactions, you have to make sure the masses on the products and reactants are the same, and the charge on the products and reactants are the same. So which of the following is false? Helium-4 is a helium nucleus. Helium is an alpha particle. Helium-4 is a beta particle. Helium is an isotope of helium. So helium-4 is an isotope of helium. And so they're all true except for the beta particle. And so it's always kind of confusing that we can talk about helium-4 as an alpha particle, helium nucleus, and isotope of helium. That's all true. A beta particle, again, is just a high energy electron. Which of the following is false? So this is a beta particle. And so a beta particle is an electron. And so it's got a -1 charge and a mass number 0. It's not massless. It still has mass. But the mass number is the number of protons plus neutrons. Electrons are 1,000 times less massive. And so this top one is true. We can symbolize a positron this way. It's got a +1 charge, mass number 0. This is also electron, a -1 charge, mass number 0. Now this one's false because a positron has the same mass as electron, and so the mass number should be 0 for a positron. And again, please remember positrons and electrons have mass. It's just 1,000 times less massive than protons and neutrons. We could also ask ourselves, what type of radiation are we most likely exposed to? And so the most likely exposure is coming from radon at 55% of what we're exposed to. 18% of our exposure is from man-made materials, X-rays, nuclear medicine, consumer product. And so it's kind of interesting. They've put aerial gamma ray detectors on airplanes to determine the radiation in the upper 20 and 25 centimeters of surface materials. And so this gives you a map. The pink or magenta corresponds to higher radioactive materials. And again, this is just in the upper 20 and 25 centimeters. The purple corresponds to the least radioactive. And this is going to, in large part, depend on the geology of the area. And from the type of gamma radiation that they're able to detect, they can determine the concentration of uranium. And so for these parts, I'm not sure how much of this is related to nuclear testing versus just geology. And so if you look at the geology of the country, you can see different types. And so we're in this region here. And so we have glacial deposits, low surface radioactivity, but uranium occurs just below the surface. Remember, the prior maps were just for the top 20 and 25 centimeters. And so you have a high potential for radon. And so this gives you the radon average as a function of county. And so Brookings, South Dakota is in a fairly high average radon exposure. So it's something we have to be concerned about. So what can happen is you can have uranium underground, and then uranium decays, eventually producing radon, which is a noble gas, meaning that chemically it's fairly inert. And so it can seep up through the ground. And if you have cracks in your foundation, you can actually get radon inside your house. And so radon gas decays into radioactive particles that can get trapped in your lungs, which actually can damage the lung tissue, leading to lung cancer over the course of your lifetime. Radon decay products are charged. Polonium-218, for example, has a charge of +2. As a result, it can stick to your lungs. Once there, it quickly emits high-energy alpha particles. Again, alpha particles are not very penetrating, but once they're inside your body, it can cause a lot of damage. Later, the polonium can actually lead to lead-214, and then there's another alpha particle. And so I should mention that often it's not just one decay activity that occurs, but you'll have a series of decays until you eventually get to something that's stable. And so radon will emit alpha particle forming polonium, which emits that alpha particle forming lead, which emits beta and gamma rays, which forms bismuth, which emits beta and gamma rays forming polonium, which emits alpha particles. And so the alpha particle is the main culprit causing lung cancer. Again, it can be stopped by your skin, but once it's inside your body, it can cause a lot of damage. Alpha particle can strike up to 100,000 atoms inside the cells of our lungs. Each atom that it hits will lose electrons, becoming ionized. These atoms may become components of important molecules in the body, or these atoms may become part of DNA, and again lead to cancer. And so it's estimated that radon is the second leading cause of cancer. Nearly 1 in 15 homes in the U.S. has a high level of indoor radon. You can actually buy radon detectors so you can test if you have radon in your home if you feel like it. I hope that was helpful.